Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the blue equilateral triangle? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. We want the area of the blue equilateral triangle ABC. Vertex A sits at the right with the base segment BC along the left, and a red segment runs from vertex B to a point D on the opposite side. Let us gather what we are told before we compute. 3 facts are marked. The red segment BD has length 3, it meets side CA at a right angle, and all 3 sides, segment AB, segment BC, and segment CA, are equal. These are the only measurements we may trust, so every step must lean on them. Because segment BD meets side CA at a right angle, it is by definition the altitude of the triangle drawn from vertex B. That altitude, with length 3, will serve as the height when we reach the area formula, so let us pin it down first. Our first insight is this: the equilateral altitude bisects the base. The altitude splits the whole into a top half, triangle ABD, and a bottom half, triangle CBD. The two are congruent mirror images, and together they rebuild the full blue triangle. We will work inside the bottom half, triangle CBD. Every angle of an equilateral triangle is the same, and 3 equal angles must add up to 180 degrees. Dividing 180 by 3 gives 60 degrees for each. In particular, the angle at vertex C measures 60 degrees. That 60-degree corner at C is shared by the right triangle CBD, since side CA and side CB both start at C. Carrying this angle into the right triangle is what lets us bring in trigonometry. Now the right triangle CBD is fully described. It has a right angle at the foot D, a 60-degree angle at C, and the full side CB as its hypotenuse, which we will call X. With one side and one acute angle known, trigonometry can find X. The sine of an angle in a right triangle is the length of the side opposite that angle divided by the hypotenuse. We choose sine because it connects the angle at C directly to the altitude and to the side X we want. Looking across from the 60-degree corner at C, the side opposite is the altitude BD, which is 3. The hypotenuse is the side CB, which is X. Naming these two pieces sets up the equation. A second insight now finishes the structure. Sine 60 links the altitude to the side. The sine of 60 degrees is the exact value root 3 over 2. Replacing the sine with that value gives root 3 over 2 equal to 3 over x. Now, it is pure algebra to isolate x. Cross-multiplying clears both fractions. Root 3 times x equals 2 times 3, which is 6. So root 3 times x equals 6. One division away from x now. Dividing both sides by root 3 isolates x, giving x equals 6 over root 3. A root sitting in the denominator is untidy, so we clean it up next. Multiplying top and bottom by root 3 turns the denominator into 3 and the numerator into 6 root 3. 6 root 3 over 3 simplifies to 2 root 3. So each side of the equilateral triangle is 2 root 3. To find the area of the full triangle ABC, we take side CA as the base, now known to be 2 root 3, and the altitude BD as the matching height, which is 3. Base and its perpendicular height are exactly what the area formula needs. The area of any triangle is 1/2 of the base times the height. We now substitute our base and height into this template. Substituting gives 1/2 times 2 root 3 times 3. Every symbol is now a number, so we simplify the arithmetic. 1/2 of 2 root 3 is just root 3. Since the 1/2 and the 2 cancel, that leaves root 3 times 3 to finish. Root 3 times 3 is 3 root 3. So the area of the full blue triangle works out to 3 root 3. Let us confirm this with a second independent method. There is a direct formula for the area of an equilateral triangle, root 3 over 4 times the side squared. We already found the side is 2 root 3, so this gives an independent way to check our answer. Squaring 2 root 3 gives 12, and root 3 over 4 times 12 is 3 root 3. Both methods land on the same value, so the answer is confirmed. So the answer is 3 square root of 3. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.